Welcome back. Today we're going to finish off our trigonometric functions unit by taking a look at instantaneous rate of change. If that sounds familiar, it probably should. We actually covered that when we were talking about polynomials. Everything about it is pretty much the same idea. We're just going to apply it in a slightly different way today. I do want to point out that today's lesson is going to feel less like you're learning a math skill and more like you're just solving a problem because it's exactly what we're doing. Um, Basically, nothing we're doing today is going to be new, or at least it's not going to feel like it's new. But we're going to see a whole bunch of ways that we may not have thought about things before. So let's take a look at the problem for today, which is going to involve a Ferris wheel. Ferris wheels are, of course, popular things to cover when you're doing trigonometry, because as they turn, the height of anything on the Ferris wheel basically just goes up and down in a repeating pattern, which is sinusoidal. In this particular question, the height of a Ferris wheel car can be modeled by the function height at time t is equal to negative 20 cos pi over 60t plus 25, where h is the height of the car above the ground in meters and t is the time in seconds since the ride starts. Part A. What is the period of the Ferris wheel's rotation? Okay. I'm going to remind you that there actually is an equation for that we saw in one of the previous lessons. And it was period equals 2 pi over k. And similarly, you can rearrange that to say k equals 2 pi over t. But in this case, it's going to be 2 pi over k. K itself is pi over 60. Cancel out those pi's. Multiply top and bottom by 60. 60's cancel. And we're left with 120. So the period of rotation will be 120, and we're measuring it in seconds. So that will be our answer. Part B. At what time is the car closest to the ground, and what is the height? Okay, thinking about what cos looks like. Cos looks like this. But we also have this negative sign up here in front of it, which means that it's going to look like that. And so it's actually going to be at the ground level, or the lowest point, right off the bat at t equals 0. What will its height be? Again, looking over to our equation here, our cos has a coefficient of negative 20, and we have a vertical translation of 25. That means the middle of the cartwheel will be 25 meters above the ground, and from there it will fluctuate up 20 or down 20. So its lowest point is going to be 25 minus 20. So basically 25 minus 20. Which is 5 meters above the ground. Which is actually pretty high for a Ferris wheel to start. 5 meters off the ground is like 2 stories. No one said math questions had to be super realistic. At what time is the car at the top of the Ferris wheel, and what is its height? There's a whole bunch of ways we could do this, but the easiest ways are usually just to logic your way through it. If it starts off at the bottom at 0 seconds and it takes 120 seconds to go around once, it should take 60 seconds to go around halfway. So basically for the bottom to go to the top. Makes sense? You could have also solved, if you wanted to, pi over 60t. This will work when that is equal to pi. Divide both sides by pi. 1 over t equals 1, and t equals 60. So we could have solved it algebraically or just using straight up logic. Similarly, what's the height at that time? I could plug in t equals 60 and actually calculate out what h of t is. Or I can just say it's 25 meters and it fluctuates up and down 20, so its maximum height is going to be 45 meters. Yeah, that is a big Ferris wheel. For part D, the radius of the Ferris wheel, we actually could have answered this right off the beginning. It's just going to be 20 meters because that's how much the middle of the Ferris wheel fluctuates between the top and the bottom. Basically, it's our coefficient, or our A value, if you will, in our equation. What is the speed at which the Ferris wheel car is moving in meters per second? Now this one here is actually pretty much nothing to do with trigonometry, but it's straight up logic. I'm just going to remind you that a speed is equal to a change of distance or over a change of time, or just how far it travels over how long it takes to travel it. For those who aren't familiar with the triangle, that's just a capital letter delta from the Greek alphabet, and it means change of. Now in this case, I'm just going to do a little aside here. The circumference of a circle is 2 pi r, and we're told that this particular Ferris wheel has a radius of 20, which we figured out in the last step. So its circumference is just 40 pi. So the distance traveled to go around the outside once, so basically if you think about a point on the circle and it goes a full 360 degrees, it will have traveled 40 pi in 120 seconds, or 40 pi meters in 120 seconds. And since no one wants to know speeds as multiples of pi, we pull out our calculator and do 40 times pi divided by 120, and we get out 1.047. And just for the heck of it, I was going to take a few more decimals, but I don't think we need to. I'm going to make a little note of that. That number, despite the fact that it looks random, looks familiar to me. We'll come back to that idea later. Okay, so that's the speed of the Ferris wheel if you're in the car. For part F, we want to use the secant method to estimate the rate of change of height at different times. Now I want to point out that the rate of change of height is also a speed, but it's not the speed of the Ferris wheel going around, it's the speed of the height changing. So there's going to be a couple things that I can point out just based on logic, and that's that at 0 seconds, I'm just going to draw a Ferris wheel over here for a moment. Down here at 0 seconds, the Ferris wheel is going to be moving this direction if I draw the tangent to the circle at that point. So what's the rate of change of height of something moving to the right? The answer is it's not changing height. So we should expect a value of approximately 0. Now, of course, our secant method is going to be approximation anyway, but it should be approximately 0. How did we find this using the secant method? We do basically a change of height. So a change of height would be a height at a time just slightly larger than 0 and 0. So I think we can get away with 0.01 minus the height, that's messy, minus the height at 0 over 0.01 minus 0. So that's looking at where it is here and a point very, very, very close to there. In fact, 1/100th of a second later. So even though that's technically not instantaneous, it's a pretty small interval, so it's going to approach the instantaneous. Again, hopefully you recall this from back when we did polynomials. So now we have our formula. So this is going to be negative 20 cos pi over 60, 0.01 plus 25 minus, I'm going to put actually square brackets around this just to make it a little bit more obvious, minus the same thing at 0, minus 20 cos. Just to save us a little bit of room there, when I put 0 into the bracket, pi over 60 times 0 is just 0. plus 25, all divided by 0.01. Now, just because the space on this is a little bit tricky, I'm going to try and shorten out my writing a little bit. The 25 and the minus 25 cancel. And so this is really going to be negative 20 cos pi over 60 times 0.01, blah, 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 blah. When I punch that into my calculator, I get out negative 19.99999726 plus 20 over 0.01. And that top number is 0 point many zeros before you hit anything. This is effectively 0. So as predicted, the answer we get is extremely close to 0 meters a second because we're moving horizontally instead of vertically. So there's no change of height. I don't want to have to redraw this Ferris wheel all over the place, but I will show you that if it takes 2 minutes to go around, it will be at the top at 60 seconds. It'll be at the side at 30 seconds, and it'll be halfway between the bottom and the side at 15 seconds. And we're going to actually find the speed at 15 and 30. So let's do the same equation for two numbers, 15 seconds and a little bit over 15 seconds. So 15.01 minus h is 15 over 0.01 minus 0. That's going to be that same big nasty equation again. At least this time we don't have the Ferris wheel diagram, so we've got a little bit more room. But that's going to be negative 20 cos pi over 60 times 15.01 plus 25 minus negative 20 cos. Again, I'm just going to kind of take a little shortcut here because I could do pi over 60 times 15 in my head is pi over 4. All over 0.01. The 25s do cancel it again. So I just plug in the rest of that stuff in my calculator and see what happens. And voila, I'll be honest, I paused the video and calculated and wrote it down because there's no point in wasting your time. But you would get that as well, hopefully. And our answer in the end is that at that point, it's moving at 0.74 meters per second in an upwards direction. It's actually moving at the 1 point whatever it was, but some of that is moving sideways and some of it's moving up. Now at 30 seconds, again going back up to our diagram, 30 seconds it's moving directly upwards. So I'm going to predict that if we actually solve this using the proper method, we should get out this number, 1.047 meters per second, which we got in a completely different way, by the way. So let's try that. So we have height at 30.01 minus height at 30 over 0.01 minus 0. Plug in the 30.01. So negative 20 cos pi over 60 times 30.01 plus 25 minus negative 20 cos. Now this one's going to be pi over 60 times 30, which is just pi over 2, plus 25, divide by 0.01. Cancel out the 25s because we can. It makes things a little faster. And yeah, you probably guessed it. I'm going to pause it, and I'll be back in a moment. And there we go. Once we plug in our numbers, we got 1.047 meters per second. 1.047 meters per second. Now I mentioned up here that number looked familiar, and it wasn't because it's the same answer as the one we got below. There's another reason. Of course, we'll have to reveal that in just a moment. Okay, so can we use this to predict the rate of change of speed at the following times, at a whole bunch of times? Now, you just saw that this is a very tedious equation. We don't want to have to do it constantly, but I'm going to show you a little trick. I'm going to redraw the Ferrous wheel right here. And I'm going to label a few points. This was 0 seconds. This was 30. This was 15. This is 60. This would be 45. This would be 90. Halfway between there would be 75. Halfway between there would be 105 seconds. And then we're back at the bottom at 0 or 120 seconds. Okay, so how is that useful? Well, if we know that it's 0 meters a second change of height there, it's going to be a 0 meter per second change of height at 60 seconds. And we know that it's the 1.047 here, but it's also going to be 1.047 here. The only difference is it's going to be down. It'll be the same speed, but moving downwards at that point. At 15 seconds here, actually let me use a different color. At 15 seconds right there, the speed was, we got that up here, 0.74, but it'll be the same speed here, at least the same upward speed there. It'll just be heading up and left instead of up and right. It'll be the same speed here and here as well, except that it'll be down because we're moving downwards in height. So then we can really quickly say at 45 seconds, it's going to be 0.74 meters per second. At 75, it's going to be negative 0.74. At 105, it's going to be negative 0.74. And at 120, it's back to 0, so that's going to be 0 meters a second as well. So that let us use what we'd already done with just 3 calculations to make a whole bunch of predictions. And those predictions are correct, by the way. They're not just, we didn't just make that up. They actually do work. Okay, so now we're going to take that and we're going to do something completely different with it. Something we've already done in the course, but something interesting. Because it's tedious and time consuming to do this equation here for every value we want, can we come up with a function that actually represents the rate of change of height of h of t? So it's not just going to give us the value at 1 or 2 or 3 points when we calculate it, or in this case, it gave us another 1, 2, 3, 4, 5, 6 points that we know. Can we come up with a function that we can plug in any value for t and find out what the rate of change will be, or what the speed upwards will be? And the answer is, I think we can. So what we're going to do is we're actually going to use Desmos to plot those points. So I'm going to switch over to Desmos and start plugging in those points. And of course, I'm going to cheat just a little wee bit in the sense that I've already been over in Desmos and I've already set it up with the proper axes, basically to make sure that our graph does go from 0 to 120, since that's going to be our time, and that's 1 rotation, and that our Ferrous wheel, which goes from 5 meters up to 45 meters, was it, will fit on this graph. So here's what I want to do. I'm going to plot in these points that I have. So I had points at 0 seconds. We have a speed of 0. What I'm going to just cheat and change colors because it's more interesting. And then we said at 15 seconds, it had a speed of 0.74. And then at 30 seconds, it had 30 seconds, it had a speed of 1.047. And I think you can see that this is going to be a little tedious, so I will pause it and punch in the rest of the points. Okay, I have finished plugging in all those points, and it occurred to me that I set up these axes almost correctly. The x-axis, or in this case time axis, is correct. But I'm not actually looking at the height of the Ferris wheel, I'm looking at the speed upwards of the Ferris wheel. And that is between negative 1.047 or something and positive 1.047. So I'm just going to change this from negative 2 to 2. And we'll go up by 0.1, I think, should do it. Oh, I did the wrong thing. Just a second, I'm going to fix it. I always do that. I go to change my y-axis and change my x by accident. So my x-axis is still going from 0 up to 120, which is good. My y-axis is now bouncing back and forth between plus and minus 1 and a bit. Okay, so now time for the big reveal. Let's put the dots on and see if there's a pattern. I really hope there's a pattern. Okay, there should be a pattern. What happened at 75? Something went wrong. I think I know exactly what I did. 75, that should have been a negative. Because we're in the second half of the ride, we're going downhill. There we go. Now there's a pattern. What does that pattern look like to you? Take a second and think about it. If you say a sine curve, I agree with you. So let's see what happens if we put in y equals sine x. And, ooh, that's not right. So one thing we're going to have to change, there's actually a few things we have to change. I don't think we have to worry about a vertical translation. I don't think we have to worry about a phase shift at all. But we do have to deal with the fact that the period of this is not 2 pi, it's 120. So that means I'm just going to put this in here. So we want it to be a k value that makes the period 120, and we have to put a k value in that's equal to 2 pi over t. So 2 pi over t, which is 120, and let's see what that looks like now. Okay, that's pretty good. The only problem is that it doesn't go through these points quite exactly, because it goes through 1 and our speed is actually 1.047. So let's give it an amplitude of 1.047. And I think you'll notice that even if we zoomed in a lot, this curve is going through all of our points. So we just came up with a mathematical model to represent the rate of change of speed of the Ferris wheel at different times. At least the rate of change of speed upwards, the rate of change of height. So now we can go back and write that equation in to our sheet over here. Which is, what do we want to call it? I'm going to call it speed at time t. It's technically speed upwards. We can call it whatever we want. And it's going to be 1.047 sine. We said 2 pi over 120, which is the same thing as pi over 60. Wait a second. Pi over 60 is exactly what we had for our original function period, which makes sense. It should have the same period. It's repeating every 120 seconds, just like it did before. We had no phase shift, so we're good to go. There is our model. So now, without having to do a long, tedious calculation, I could plug in any time I wanted. I could plug in 5 seconds, 8 seconds, and very quickly get out what the rate of change of height will be. That is pretty cool. What's even cooler is that there's calculus that can get you that answer much, much faster than we just did it. In fact, I'm going to show you a trick. I'm not going to teach you calculus today because, I mean, we're already like 25 minutes in. I don't think it's fair to try and teach you calculus in the next 3. but I will show you kind of how it works. So what I'm going to do is there's a web page here that lets you find something called a derivative. And you'll learn how to do derivatives in calculus. For this particular function, the derivative's actually really, really easy. But I'm just going to go and use the online calculator to do it right now. Okay, so going over to that particular website there, and by the way, there's lots of these. I just chose this one because it was easy to find. It lets me find the derivative, and in calculus, you'll learn that the derivative is just a way of saying what is the slope of the function at different points. So what we have to do is actually type in what our original function was, which was negative 20 cos pi over 60, and unfortunately this is linear, it's not like an equation editor. It shows it below, but where I punch it in, it just has to punch in this way, times x, because it doesn't like t, and plus 25. So there's the equation that we had, and if I scroll down just a little bit, it explains what it did, but it's actually easier than that. Oop. Oop, where's my answer? Go. Okay, if I scroll down here. Okay, it says this is the derivative. Other than the fact that it's written a little bit differently, that's pi over 3 sine pi over 60x. I'm going to just write that down on my sheet of paper here. Pi over 3 sine pi over 60x. Okay, switching back. Does that not look a lot like exactly what we got doing a lot more work? Like a lot more work? Pi over 3, and that's why I said this number looks familiar. That's actually pi over 3, exactly, if I wanted to be really exact. Sine pi over 60t. Now this notation here, that's calculus notation. You do not need to understand it at all, but I think it's interesting to mention that the notation actually makes complete sense. And most calculus teachers don't even mention this. In calculus, most teachers would read that as dh divided by dt. And that's not a d. They often draw a d just because that's a little bit harder to draw. If you're not familiar, that symbol is actually a delta. Remember back when we saw speed is equal to delta d over delta t? Well, what that really means is a change of distance over a change of time. This is a change of height over a change of time. And the delta, the lowercase delta, signifies that it's a little change of height over a little change of time, which is what we did with our secant method. We let it be a very small change of time, which caused a very small change of height. And you can actually get this result very easily using calculus. That's about a 5-second calculation if you were given that on a calculus test to get from the original equation to that one. I won't show you how to do it because that takes away your calculus teacher's fun, but that's it. And then we can use that function, which is correct, if we want to actually go back and just find the exact values at 0, 15, and 30 seconds. We already did this the long way using the h at 0 plus a little bit over or minus h at 0, etc. But it's actually a lot faster to just say that the speed or change of height is pi over 3 sine 0. Sine of 0 is 0. This one is pi over 3 sine pi over 60 times 15, which is sine of pi over 4. Sine of pi over 4 is actually 1 over root 2. And if I pull out my calculator, pi divided by 3 times 1 divided by, oops, wrong button, pi divided by 3 times 1 divided by root 2 equals 0.74048. So that's where we got the meters per second, 0.74 meters per second before. And 30 seconds if we punch it in, pi over 3 sine pi over 60 times 30, which is pi over 3. And inside the bracket there, pi over 60 times 30 is pi over 2. And sine of pi over 2 is 1. So pi over 3, and we already said pi over 3 is the 1.047 meters per second. So what you're going to see is that calculations that take us a significant amount of time can be done very quickly using calculus, and computers can do calculus fairly easily. So for programming, you definitely want to be able to understand how calculus works and punch it in. Okay. Other than that, the only way you're going to get really any better at this is to practice it and to try it with different applications and different situations. So there's a few questions to try tonight. There's not that many because some of these are a little bit tedious. I think there's 4. 2 of them are actually examples that are fully done in the text. So basically, I just want you to go through and try to mimic them. Look back at the examples as much as you need to, but try not to look at them more than you need to. You'll learn more that way. And then there's a couple that you can try after that. If you have issues, let me know. Otherwise, I will see you in the next lesson, which will actually be the next unit. See you later.